The last general problem-solving strategy I will talk about in this module is branch and bound. Let's dive right in. Remember the combination log from the clip about brute force. The set of all possible combinations, or solution candidates, can be illustrated as a tree, with the top node representing the completely empty solution with no digits set. We can let each level in the tree represent a digit in the combination log. For the first and rightmost digit, we have 10 possible values. These each correspond to a branch in the tree. Assume that we set the first digit to 0. Then there are 10 possible values for the second digit too. We could also choose 0 for that digit. For the third digit, we would have 10 choices, 2, and so on. We could also have chosen 6 for the first digit, and 2 for the second, and so on, all the way down to digit number 5. So each solution candidate corresponds to a path from the root node to a bottom node. For each level, the previous number of possible combinations are multiplied with 10, resulting in 100,000 combinations in total, as we have already discussed. Given a partially constructed path from the top node, which corresponds to a partially constructed solution candidate, the strategy of constructing all possible partial solution candidates for the next level is referred to as branching. But imagine if we, at an early point, could conclude that one of these nodes would never lead to an acceptable solution. For example, if we could conclude that all solution candidates that will be generated from this 2 branch will never be acceptable, then we could avoid considering all the combinations that will come from the subtree below that node. In this case, it would be 1000 solution candidates that we did not need to consider. If we could reject the 6th branch from the previous level instead, we would save 1000 solution candidates from each of the 10 branches below. That is, we could avoid considering a whole 10,000 solution candidates in that case. In the branch and bound strategy, this is the bound part, namely to come up with a bound for the best possible solution quality for each branch. If the bound is worse than the quality of a solution we have already found, then there's no reason to investigate that branch and all the solution candidates it covers. Let's try to solve a concrete problem using the branch and bound strategy. Consider a bunch of people. Let's call them agents. Also consider the same number of tasks that we have agents. Here we have 4 agents and 4 tasks. In order to be able to refer to both the agents and the tasks, let me associate them with letters and numbers. Each agent can solve each task with a certain cost. If an agent can't solve a specific task, we could set that cost to infinity. Here is the costs for each combination of agents and tasks. The problem is now to find exactly one assignment of each agent so that the total cost is minimized. We will start with the empty solution where no agent is assigned any task. We also need something to compare with as we begin constructing the solutions. If we have no clue about what can be achieved, we could set the best cost found so far to infinity. Then it will be updated whenever we find the first solution candidate. In our case, however, we can find a solution relatively easily, namely by blindly choosing a task for each agent, for example like this. The sum of all the costs of all these assignments is 10, so let's write that cost as the best so far, and also write which assignment that led to this cost. In the tuple written here, the first value denotes the task assigned to agent A, the second value denotes the task assigned to agent B, and so on. We begin with an empty partial solution candidate with no assignments made. And then we will build a tree like the one we saw on the previous slide. Notice that the tree is only a conceptual thing to show how all the possible combinations are constructed. Each level in the tree will correspond to an assignment of a task to a specific agent. So in the first layer, we will look at all possible assignments for agent A. In the next layer, we will consider all possible assignments for agent B, and so on. So for agent A, there is 4 possible task assignments, namely task 1, 2, 3, and 4. First, we try assigning task 1 to agent A. We now need a bound on how low a cost we can possibly achieve given the current assignment. We can get such a bound by always choosing the lowest cost for each of the yet unassigned agents. For agent B, 3 is the lowest possible cost. For agent C, 1 is the lowest possible cost. We are not allowed to assign the same task to multiple agents, but that doesn't matter when we try to come up with a lower bound. If we select the smallest but possibly invalid assignment of cost 1, then a valid assignment will be larger than 1. So in any case, we can't get it cheaper than the cost of 1 for this agent. For agent D, the lowest cost is 2. So 3 plus 3 plus 1 plus 2 equals 9. So 9 is a lower bound on the possible cost in the branch where we assign task 1 to agent A. I will write LB9 next to the node to denote its lower bound of 9. The next branch at the same level will assign task 2 to agent A. And all solution candidates generated below that node will have task 2 assigned to agent A. If we look at the cost table to the left, it costs an amount of 5 to assign task 2 to agent A. The cheapest possible task assignments for the remaining agents stays the same as before, so the smallest possible cost in this branch summarizes to 11. We write that next to the node, and next we consider the branch with task 3 assigned to agent A. Now the cost of agent A is 9 as seen in the cost table, and the minimum cost for the remaining agents remains. And the lowest possible cost in this branch therefore summarizes to 15. It may end with a larger cost, but we can't get below 15 under any circumstances. Last, we consider the branch where task 4 is assigned to agent A. That assignment has a cost of 2 according to the cost table, and with the remaining agents' minimum cost being the same as before, the total minimum possible cost for this branch summarizes to 8. This is how we branch out on all possible assignments in a specific level. We choose an assignment and calculate the bound associated with that assignment. Already now we have some interesting findings. The fully valid solution that we found before had a cost of 10. So when we have a partially created solution candidate for which we know that its cost can never be smaller than, say, 11, which is greater than 10, then there is no reason wasting time building on top of that. We can therefore stop working on branch node 2 and all the many solution candidates that would have been generated below it. Similarly, there is no reasons to continue our exploration of branch node 3, which lower bound is 15. At this point, 2 nodes remain interesting, namely the 1 branch and the 4 branch. The blue box in the lower left corner holds a tuple representing the agent assignment for the former case, and you can see that only the first tuple position for agent A is set. The box also contains the lower bound for that node. Now we need a container to store all our unfinished solutions. In this case, we will use a priority queue that sorts the incoming elements according to their lower bound. Then we can easily retrieve the element with the smallest lower bound, which is the element that is the most promising so far. Notice that there is a touch of a greedy algorithm in this approach. We will also store the partial solution candidate for the 4 branch with the lower bound of 8. Away with that. And now we will continue our exploration from the most promising nodes so far. Let's ask the priority queue. The 4 branch. From here, the assignment of task 4 to agent A is fixed, and we therefore continue to the next level representing possible assignments for agent B. Here are 3 possibilities because we have already used task 4. So in this branch, the cost for agent A is fixed at 2. First, we consider the assignment of task 1 to agent B. This has a cost of 9. Like before, we then produce a lower bound for the node by using the smallest possible cost for the yet unassigned agents. That is 1 for agent C and 2 for agent D. The sum of these costs is 14. 14 is larger than 10, which was the cost of the best found valid solution so far, so we can immediately skip it. Next possible assignment for agent B is task 2, which has a cost of 3. The remaining costs stay the same, and the sum is therefore 8, which is smaller than 10 and therefore still relevant. Similarly, the 3 branch assigns task 3 to agent B. That assignment also has a cost of 3, so the lower bound of that branch is therefore equal to the lower bound of the previous branch. Here the last 2 solution candidates are interesting. So here is a box representing the first solution candidate with an assignment of task 2 to agent B and a lower bound of 8. This is put into the priority queue, and so is the solution candidate from the 3 branch. Let's ask the priority queue which node to extend next. The most promising node so far is the bottommost 2 branch. For this branch, task 4 is fixed to agent A and task 2 is fixed to agent B. Now there are 2 remaining options for agent C at the next level, namely task 1 and 3. If task 1 is assigned to agent C, the cost of the assignment is 1. And just like before, the cheapest possible assignment for the remaining agent, D, has a cost of 2. Therefore, the lower bound of this branch is 8, which is the sum of the shown costs. If we assign the task to agent C, the cost of that assignment is 2, and the total cost sum is therefore 9. Both solution candidates still have the possibility of being cheaper than our current solution with a cost of 10, so we store the first solution candidate in the priority queue and the next one. The next node to explore, according to our priority queue, is the 3 branch from level 2 of our branch tree. Here task 4 is fixed to agent A and task 3 is fixed to agent B. 2 options for agent C, namely task 1 and task 2. If we choose task 1, the cost of that assignment is 1, and the cheapest possible cost for agent D is still 2. The sum is 8, so the solution candidate from this branch can never be cheaper than 8. If agent C is assigned to task 2, that assignment has a cost of 4, and the total sum is therefore 11. Here only the first branch is relevant, because the second branch has a lower bound of 11, which is larger than the cost of 10 of our already found solution. Here is a representation of the first branch. Let's store that in the queue for further exploration. The next node to explore has task 4 assigned to agent A, task 2 to agent B, and task 1 to agent C. Here are the corresponding fixed costs. There is now only one task left to agent D, namely task 3, with a cost of 7. Now we actually have a complete solution candidate, but its total cost is 13, and it's therefore irrelevant. Let's ask the priority queue for the next node. In this node, agent B is assigned to task 3 and agent C to task 1. The only task left for agent D is task 2 with a cost of 3. The corresponding complete solution has a cost of only 9. And this is actually cheaper than our current best solution candidate. We therefore replace the best so far cost with 9 and write down the tuple representing the solution. Let's proceed to the next partial solution candidate from the priority queue. This solution candidate represents the assignment where agent A is assigned to task 1 and no other assignments have been made. Since we already have a complete solution with a cost of 9, there is no reason to extend that branch. The next solution candidate assigns agent C to task 3, but this candidate also has a lower bound of 9, so with the same arguments as before, we will skip it. Now the priority queue is empty and the best found assignment cost is 9. Let's talk a bit about the complexity of solving this problem. Assume that we have n agents and therefore the same amount of tasks. If we were to solve the problem using a brute force strategy, where we iteratively generate all possible solution candidates, then we would have n possible task assignments for the first agent. Then, with that task taken, we would have n-1 tasks to choose from at the second agent, n-2 tasks for the third agent, and so on, until we only have one task left for the last agent. This is also known as the faculty of n, and that number explodes in size when n grows. It's not possible to give a similar general complexity description for the branch and bound approach, for the possible complexity reduction is completely dependent on the concrete problem to solve and also on the bounding function. If we cannot bound efficiently, then we cannot cut away large parts of the branch tree, which is what gives the largest savings in computation time. In our case, however, we had a good bound, and therefore we were able to cut away the majority of the branch tree. I have included an implementation of the branch and bound example that we just went through in the source code that comes with the course. Branch and bound is a very general solution strategy, which can be applied to a vast amount of problems. One general case is whenever we have a number of placeholders into which we can place a fixed number of things. If each such assignment comes with some sort of cost or quality measurement, we can probably come up with a bound. One example is our combination log, but with some constraints on the digit patterns for the final number. We just saw the assignment problem, and even the 01 knapsack problem that we covered in the part about dynamic programming could have been solved using branch and bound. Another general class of problems concerns choosing good subsets from a larger set. In machine learning, for example, branch and bound can be used to choose relevant features for constructing a model, and the strategy can be used for finding the shortest path in a graph. Yet another category of problems concerns making configurations. For example, arranging smaller boxes into a larger box, which is equivalent to arranging packages in a container so that all packages fit within the container. The last category is a bit different. If we have a huge problem and are not necessarily interested in the absolutely best possible solution, but is satisfied with a solution that is good enough, then we could calculate 2 bounds instead of just one at each branch. A bound for the best possible and worst possible solution at the branch. Then we can stop the computation when the 2 bounds are sufficiently close to each other, because that would mean that the real and optimal solution would be within these 2 bounds.